So now I would like to welcome Mr. Krishnan Rana, Executive Vice President of Agmatel India, and Mr. Anish Mukherjee, Subject Matter Expert from the NVIDIA Corporation, to enlighten us on the crucial topic of optimization of AI models. So I just read the brief bio. So Anish is a solution architect working in NVIDIA. He's working on interference optimizations. Anish has master degree from TU Delft and a bachelor degree from VIT. Okay, so we welcome him for the talk. Thank you.
Hi everyone, good morning. Thanks for welcoming us to this session, and I'm very pleased to be here. Thanks to DRDO for sponsoring this event, and it gives us immense pleasure to get this platform to come between you and share our experiences from the industry. And very grateful thank you to NIT Delhi as well for extending us this opportunity, and to Agmetal as well, our solutions partner. And Rana sir is here, and he'll be giving you a brief about his company, Agmetal.
I know we are running short of time. I'm not going to take much of your time. Just to quickly introduce as Agmatel, we are a very young organization in the field of information technology, just 34 years old in this domain. We are having association with NVIDIA for catering HER, higher education and research part of it. We are working together in a lot of education institutes for setting of AI labs, for Center of Excellence, and in fact in few universities as well, AI universities. So, Amish, what I suggest you can go on because these are students.
Sure.
You know, I want you should show them actually live stream part of it, the actual truth about AI and how these guys can do and help not only for yourself, for entire country. Thank you.
Thank you. So I'll start my talk. So my talk is centered around inference optimization, and why inference optimization or even training optimization becomes a very critical part of the whole AI ecosystem that we have today. So I'll just start with a brief introduction of the landscape of AI that's right now out there. So as we know, AI again is a very broad term. Under this term, there are many terms such as machine learning and deep learning, and right now we have generative AI. So the whole trend started from deep learning. The first paper that came out in backpropagation in 2012, and after that we are seeing incremental developments, and the whole this race of generative AI started from 2018 with the seminal paper Transformers or Unit, and that kick-started this whole thing. And all the LLM models, the biggest and the brightest model that we have right now, whatever we have, it runs on some form of the transformer architecture that is running under the hood. And transformer architecture is a very compute intensive architecture. I'll be throughout the talk just showing you how much compute is required, and today also the problem is we are not bounded by compute. We have enough compute, but it is the communication that is, or the memory that is the bottleneck, because you need to transfer a lot of data inter-system. This is inter-system communication that I'm talking about. So you need very high bandwidth data transfer, you need very high bandwidth memories. So throughout the talk, I will be exploring each of these challenges and the bottlenecks that we have, and how we have technologies to address these. So why did we started seeing this boom, and why right now? So a mixture of combinations happened, and together it is being a driving force behind this whole generative AI revolution that we are seeing right now. So we have the right amount of data with us right now. So you need trillions of tokens to train a model like ChatGPT. So we do have common crawl internet data available, synthetically that data set has been augmented, so we have the right technology to curate data and to use that data for training. We also have had the developments in the algorithm space. So it all started out from backpropagation. Backpropagation, if you look at the basics, it's a chain rule derivative. And then from there, you had your transformers. Transformer, again, we had some incredible innovations in the field of matrix multiplication, because if you look at the transformer architecture, at its core, it's just matrix multiplication. And any company in the world who is working on accelerating AI, at the core of it, they are just doing plain matrix multiplication acceleration. How we can multiply matrix fast is what all AI acceleration is all about. So you have different type of processor that came up. So CPU does everything sequentially. CPU is not built for those tasks. So hence GPU became popular because you can fragment that problem and offload parts of it. And CPUs and NPUs are becoming more and more mainstream right now. The reason being because they are fundamentally different on the level they do their compute. So they make use of instruction set parallelism as well. At the hardware architecture level, you have instruction level parallelism, wherein you have long complex instruction set. In one instruction set, you can issue multiple instructions such as two load instruction, one store instruction, one maximum instruction. So you can build a pipeline code, and that helps you make your systems run faster. So all these innovations, they happened in the technological space and the compute space. And plus you had the availability of data, and all of this together is fueling the AI development right now. So right now, where do we stand in the whole landscape of generative AI? Most of us, we are very familiar with what ChatGPT does. You ask a question and you get back an answer, or you can, the new Llama integration in WhatsApp, what Meta has done right now, you can even send out a query and then get a generated image from that. But the capabilities lies beyond that. You can embed any information space into a latent space, be it your protein, because protein also has a language. The DNA sequence, they are built out of your 4 fundamental blocks. So you can encode any information and put that in a latent space, and the output can be anything. So you can think of a video generation and you can ask the AI to explain that. So you can feed your input becomes a video stream, and your output becomes text. So that's the multimodality that's unique to what GenAI is bringing to the space right now. Because before that, all the supervised models, they were very hyper-focused. Wanted to do image processing or image-related tasks, you have convolution neural networks, they had ResNets, and they are doing some specific image classification tasks. So you had to generate data, label data specific to that use case. And it can only do that task and generalize to that particular subtask as well. But this is changing the whole paradigm of how we are doing AI altogether. So now talking about the compute requirement, because as ma'am was rightly saying, the reason why India also missed the bus on generative AI again is also that India as a nation, the compute requirement what these developed nations have right now, that's the reason why they were able to drive the entire AI, I would say, frontier. And India is also working very actively in building up the compute infrastructure. The government of India is working tremendously to make sure that India is capable and India becomes the AI capital of the world. So the reason why compute is such an important part of this entire story. As you can see, this is the training compute requirement. So in terms of petaflops, how many petaflops of compute was required? If you see till the point, the inflection point becomes somewhere close to your the time around 2019 when BERT was there. after BERT, the moment you laid the foundation for your large language models, you can see how tremendously there was the inflection point and how the compute requirement is increasing. And before Transformer, the compute requirement doubled 8 times in 2 years, and now it is growing at a 256x in that 2-year cycle. So that's why compute becomes such an important part in this whole story. Now I'll start covering some specific areas. Why do you need optimizations? So I'll start with, again, the story around why supervised learning has its limitation. While it served us good, but it cannot scale. The reason being, the first is the power law. If you look at this graph, this is a log scale graph, and the amount of data that you need to reduce your generalization error is incredible. And you start out, you require less data. You grow out your models, you start requiring more and more supervised data, but the incremental gains that you are getting start diminishing. So you generate from 0 to 10,000 data set, you get a good start. But from 10,000 to maybe 1 lakh, you expect, okay, the scale would continue, but it is giving you very diminished returns. So first of all, it is very hyper-focused. Second, there is diminishing return that kicks in due to the power law limitation. And the second reason why supervised learning cannot just continue is labeling data is a massive problem. So anyone who has worked in the space of machine learning, they would definitely understand the pain of getting labeled, curated, good data that they can start ingesting for their work. So I'll have a few examples. Let's say if you're building a self-driving car system, it is very difficult to just generate data and then label the data, because you require a tremendous amount of human workforce behind it to generate labeled data. And then also domain expertise also kicks in. So let's say if you want to do some work in the domain of medical image segmentation, you need doctors. Our doctors are already stretched, and we would not want to burden them with this work. But again, this creates a bottleneck in the whole process of, if I want to implement AI, how do I get the data? If I cannot bring a doctor into or any other human specialist into the loop, how do I go about it? How does AI evolve? That led to the development of this whole generative AI paradigm shift that we are seeing, because you don't require labeled data anymore. So without labeled data, how do we train these models? So for training these models, we do implement something known as the masking loss function. So in a very abstracted form, if I just want to explain what masking loss is, you have a sentence, you feed that to the neural network, you mask each part of the word, each part of the sentence, and then you ask the neural network to predict, and then you see how much your loss is, and then you readjust your weight. You do this for each part of the sentence, each part of the word, and then you optimize your loss functions according to that. So that's why we could remove the need for labeled data, and that's why you can see this has increased the pace of AI development tremendously, where every other week you'll see some models from some company coming out and claiming that they are state of the art. And it's really difficult to keep up with the amount of AI research that is coming into the space right now. Couple of weeks back, 5.3 was the best model. Then Meta came up with Llama, then some Chinese company came up with Qwen 2. NVIDIA announced Megatron 340 billion model, claiming it's the best. And Mistral, couple of days came back with Mixtral and Coachstral. So it's very difficult to keep track of the research, and this is the whole reason why, because you do not need any labeled data anymore. You just have your common crawl data or any other data that you get from public source, feed that through the pipelines, your data ingestion pipelines, and you're good to go. So now the bottleneck is your infrastructure. The data problem you have solved, because you have established it well beyond any doubt that you cannot without even labeled data, you can scale up your AI systems. Next question, there are two remaining puzzles which still needs to be solved. One being your memory and the other being your compute capacity. So I'll be addressing the next. So as the models are getting bigger, so let's say if you have an on-prem discrete GPU that you have on your system. So if you ask this question, can I just, it's also a GPU and it's also a pretty powerful GPU, can I just do AI model training? And why would it fail? So when you ask these fundamental questions, you start getting these answers. So let's say you want to work with a 1 billion parameter model, which is a very small model in the AI space. So for 1 billion parameter model, you need 2 bytes if you are working in half precision being FP16. Your models are trained and stored in FP32. So you are already reducing the precision and making it FP16. So I'm assuming 2 byte goes there, and 2 byte goes for gradient storing while the training is happening. And for each optimization state, you need 12 bytes. So that's about, if you take a 1 billion model, just for training, you need roughly about 15 GB of compute memory. So, and if you look at our discrete GPUs, if you look at a 4090 system, RTX 4090, it comes with 8 GB of VRAM. So you cannot fit that model. So how do we progress beyond this? So then the whole concept of data center GPUs and doing this on multiple nodes, distributing the loads on multiple nodes, it came up. And the scale of compute is also tremendous. So if you look at this, if you just start with a 1.7 billion model on an A100 system, so a DGX A100, A stands for our Ampere architecture, and a DGX system consists of 8 GPUs. So on a DGX A100, it took for 1.7 billion parameter model, you would require 6 weeks. So per iteration is 6 weeks, still fine. Let's say I'm going towards a 1 trillion parameter model. On one DGX, it would take you 70 years. So it's just not humanly possible to run it on one DGX. So if you scale it to 4 DGX systems, it goes to 17 years. And then the compute is also becoming efficient. This was on our Ampere architecture. Going to the Hopper architecture, it boils down to a couple of days. You can train trillion parameter model well within a week. And on a maybe 256, a decent size cluster, you can tackle this in under a week's time. So you also need to keep your iterations manageable. So that's why the huge compute requirement comes into picture, and that's the whole reason why we love it, because yeah, that sells a lot of GPU and NVIDIA stocks just goes higher and higher. That's just some good news for us. Okay, now that I've addressed the problems, I'll talk about the optimization techniques that are out there and why AI compiler technology being with us for maybe 60-70 years now. But why again compilers are getting into mainstream. So I'll be discussing these things in the next section. Okay, so the first solution. Let's say if I'm bottlenecked by memory and my RTX system has only 10 GB of memory, I can very well offload it to the CPU. CPU has anyways much higher. If you look at a server class CPU, it will have hundreds of GBs of memory. So I can very well offload the tensor to the CPU, but then you are again bottlenecked by communication. Your communication will be very slow, hence your throughput will be less, and your training time or your inference time goes up. So that's why this is a very basic solution. It works, but again you need to do use case by use case basis analysis to figure out whether this is the right technique for you. It's the most basic technique out there, but yes, you can offload part of the tensor to CPU and let it run on the CPU. This technique is very focused for trainings. This is known as activation checkpointing. So what activation checkpointing does is you do not store all the activations. The reason being, some activations can be computed on the fly very efficiently. So by storing memory, we do not want to create any other memory bottleneck, because memory is very precious when we are doing AI training or AI inferencing. The whole game is how much you can optimize memory saving. So one technique, you identify those layers, maybe a JELU layer, all the element-wise operation. They are pretty easy. So all the element-wise operation you can compute it on the fly, because they do not occur so many times in the network. It will be towards the end, maybe softmax. Softmax, it will be towards the end. So the checkpoints, you figure out what checkpoints you can compute on the fly and don't store them. That reduces your memory bottleneck a little. That's one of the techniques. These two are massively important techniques. One being tensor parallelism, another being pipeline parallelism. So I'll just ask one question. So how many of you have worked hands-on with any vision model? ResNets, any basic models? So, sir, if I may ask you a question. So ResNet, let's say ResNet. So the compute block of ResNet, it would have some convolution layers followed by max pool, followed by some activation. And the reason I'm asking this question is, what happens? Like, do I want to keep all of this compute on device, on one single device? So the pipeline parallelism, because if you look at the computational graph, it's a sequential flow. So I can very well partition this computation graph, and I can put part of the compute on one GPU, another part of the compute on another GPU, and build a pipeline. So I can put the entire convolution block on one GPU. I can put the transformer block on another GPU. That's how we can run, let's say, your diffusion models. What it would do is, I'll just give a very abstracted view. So when your first set of data arrives, let's say you want to do your convolution first, and it is followed by your, let's say, transformer block. Convolution running on one GPU, and your transform is running on another GPU is the case that we have established. First set of data comes, it gets processed on one GPU, you do the convolution, then it gets offloaded to the other GPU for the transformer block. And then what you're doing is, at the same time, you can start filling up your second GPU and start doing the convolution operation for the second batch of data that is coming. So what you can do is you can build very effective pipelines. So the bigger the pipeline depth, the bigger batch size you can serve together. So that's how pipeline parallelism solves this problem, that you don't need to load the entire model onto one GPU memory. You can split the compute, and this is good for cases where you have bigger batch sizes, because only when you have enough data will you be able to form very deep pipelines. For inference, this does not hold true, because you do not know whether you'll be getting one request from one user or 100 requests. You cannot just build a system wherein you are building the system for 1,000 users and only one request comes in and you are just filling the rest of the 99 batches with just padding. You're wasting compute, and we do not want to waste compute. That is some fact that we have established. So what you do is you go to this another technique. Here what you can do is you split the conv block. You can split the conv block into smaller sections and put it onto different GPUs. And by doing tensor parallelism, what you do is you are basically computing smaller section of a bigger problem on each GPU, and then there's intra-node communication happening between the GPU. It does a scatter gather, and on one GPU it collects back the result. So basically you are reducing the latency, and on one single node what you'll be able to do, when I say one single node, it means I am talking about an 8 GPU system. That's the standard that we have at NVIDIA. So you can split a layer, and it is very good for if your model can fit in a single node. And when the reason why it does not scale out beyond one single node is because inter-node communication is extremely fast. Intra-node communication is extremely fast. So a GPU to a GPU on the same DGX system can talk to each other at 1 terabyte, more than 1 terabyte per second speed. The moment you go outside a node and a node has to communicate, the speed becomes a bottleneck, because the speed, if it's an Ethernet based system, it will be 400 Gbps per second speed, and if it's a InfiniBand, which is again NVIDIA's networking product, there you have about 800 Gbps per second speed. But your speed does come into the picture and it starts bottlenecking again. So you have to again choose between whether you want to split your single operation onto multiple GPU, or you can do a pipeline parallelism. So these two techniques are very important techniques and have been ingrained in all our compilers, and I'll be showing a demo of that later. So now what if even I have an infrastructure and I cannot fit the current models even by applying these techniques onto my infrastructure that I have built? Do I just go out and spend more money? Good news for us, but yeah, the world does not work that way. So there is very active research going in this field, and this is one of the most cited fields right now in the AI space, which is quantization. So when I say quantization, it's again a concept that comes from your digital signal processing course. So it's the same concept. You take a network, let's say when you're working with digital systems, you have an analog signal and you quantize it, and you discretize that. So that same context, we extended it. So you have a FP32 representation of a number. Quantization techniques help you reduce and represent that number without losing much accuracy in a smaller bit width. So you can represent that in FP16. We have also started representing that in FP8. And the next Blackwell architecture that we have, it will also have support for FP4. Research from Microsoft says it can also be represented in non-power of 2 formats, where you can go to FP3, but you do not have hardware for FP3. So you have a parallel thread running which converts FP3 data into maybe FP4 or FP8, and you have your optimized kernels working on FP8 data. At least the problem what you are solving is you're saving space and you are saving your memory bandwidth. You can transfer bigger chunk of, so you have a limited size highway, you can send more data through that highway. So that is what it will do for you. So right now, FP8 quantization, that is weights 8 and activation 8 quantization, is the most popular quantization out there. It does not impact your accuracy that much. And then we have FP8 kernels written for our hardware, which accelerates it even further. So quantization is definitely something everyone should be aware who is working in the inference space or the training space, because it helps you fit your model in the current infrastructure that you have. So 8 billion model, if it is requiring 14 GBs of data, it will start requiring some 6 GBs of data. Just if I'm talking about inference, an 8 billion model would be 16 billion model in FP16. At FP8 level, it would again come down to your, it can be represented by 1 bit, so 8 GB. So it is a question right now that if you do this, it will decide whether you can fit it on your device or not. Because if you have a 10 GB VRAM GPU, 16 GB model won't fit, but you're doing quantization, your model will start fitting in your 10 GB machine. So that's the reason why everyone I would highly recommend who is working out in this space, they do a little research on quantization, because that will help you and enable you to make the best utilization of the current compute infrastructure that you have. Now I'll talk some more on KV caching and attention techniques. LLMs in principle, they are autoregressive, and when I say autoregressive, it means I generate the first token, I take that first token, feed it back, I generate the second token. I take the first two tokens, I take it and feed it to generate the third token. So when you look at this model, you can already start seeing that there are huge amount of redundancies built in. How do you address that? You can again take hints from operating system concepts that have been developed in the past, you cache them. So whatever you need to reuse, you just cache them. And once you have cached it, you can again do a paste caching. The same concepts that were applied in OS does apply here also. So you do not have to declare a contiguous block of memory. You can have a paged assignment. That way again you are by ensuring you are not first pre-allocating memory and blocking it even when you don't require it. You save again space by doing a paged KV caching. Then you have streaming LLMs, and in streaming LLMs basically if you are doing a multi-turn chat, the way you interact with ChatGPT is a multi-turn way. You ask a question and you ask a follow-up question. So you retain some of the KV cache so that you do not need to recompute it. So that's one way. There's a sliding window. If you do not want to implement multi-turn chatbot, or if you want to just have a very small multi-turn chatbot, which maybe just caters to a couple of turns, what you can start doing is the KV cache that you have built, you can start flushing out in a sliding window technique. So those are the multiple, again, innovations that were done to make sure your inference becomes highly optimized and you save space. So these all techniques, they are all supported on multi-GPU and multi-node setup. So if you are running it on, let's say, a couple of GPUs, you can do a tensor parallelism on that level. If you are running it on multiple nodes, if you have a small scale data center setup that you have, you can extend that to the scale as well. And it's the same one single line of code that would run for a multi-GPU or a multi-node setup. So your code base does not change. That does not affect your development time. So another thing, optimize attention. So attention in itself is very compute heavy. On top of being compute heavy, it is very IO bound. And as someone who is working on hardware, we never want our systems to be IO bound. Because if your system is IO bound, theoretically, if your compute happens instantaneously, you won't get your outputs instantaneously because you're bound by the transfer times. So you have to optimize for that. So what we do is we write optimized kernels. So at the hardware level, you need to understand the architecture and write optimized kernels, and you have various implementations of your attention mechanism. The best and the most famous one is the multi-head attention. But then for every K, for every Q, you have a K and a V, which makes it inefficient, and the computation load is also very high. You can do away with that and have a grouped query, wherein you have, let's say, for four attention heads, you have 4 query heads, and for each of the 4 query heads, 2 of them are being catered by one key and one value head. So that way you are effectively reducing the compute. So this is one of the optimized attention techniques that you can implement. This does hit you on the accuracy front, but again, at least it lets you scale down the compute requirement by a lot. So you need to do assessment that, okay, is it some super critical application that you're building where accuracy loss would be disastrous? Then probably not. But yes, if you're just building an assistant, you can very well do this optimized implementation. So KV cache, again, when we're doing quantization, why not just extend it to quantization at a KV cache level? We very well did implement that, and you can quantize your KV cache and represent the KV cache data in FP8. So that again halves the memory requirement that you have. So that's another optimization technique that's out there. In-flight batching. So when you're doing inferencing, all your requests, I can ask a 3-liner request, maybe you can ask a 2-word request. they are not of the same size. And right now what we do is we pad everything. We pad everything. The moment we pad, we are generating useless tokens. So what we can do is this same pipelining concept, we extended it on the application layer as well. So what we did is now we have pipeline. You can see after the end of the token, the first one shows the static patching, wherein you have you determine that okay, this is the batch size, maximum batch size, maximum sequence length I have catered, and then you have your request whether it's small or big. You pad it and send it, and you generate your output. In the other one, you can see the pipeline being implemented. So after the end of token, end of sequence token, you can see the other requests can get pipelined. So it does gives you some amount of boost. So in-flight batching also becomes a very important inference optimization technique. So how do we all do this? And that's where the whole compiler comes into picture. So this is all done through our compiler, what we call as TensorRT LLM. So we have abstracted away all the complexity. You do not have to write CUDA code. You can just very well bring in your Hugging Face model or Onyx model or whatever model you work on, and you can just use this compiler, which is open source, and it will give you all the optimizations that you need to make your models run efficiently. And once you do that, the benefits that you reap is if you run a Hugging Face or model out of the box, let's say you're running Llama 70 billion model, so you get about a 9x improvement in throughput. So that's what just changing a couple of lines of code would do for you. So that way you'll be able to generate more tokens, and then also start, then your investment in NVIDIA, buying such big infrastructure also starts making sense because you can justify your TCO calculations. So I also had a demo session, and I can do that right now, but I am having some communication issues. Cannot share my screen. How would I? Sure. So I can do the demo session post lunch where I have a hands-on. Okay. Thank you all. Thank you, Anish sir, for such an insightful talk on generative AI of training and inference optimization. Now, I would like to call upon Dr. Anurag sir to present a memento as a token of appreciation to Dr. Ranjana and ma'am. I would also like to call upon Dr. Prashant sir to present a memento as a token of appreciation to Mr. Anish Mukherjee.